now. You can bomb it if you want. Hi guys, this is about thermodynamic processes. Ready? Quick and easy. So how does this work? That's your title. Okay. So there's two types of processes. I'm just going to get right to it. There's isochoric. Well, sorry, we're going to encounter about 4 or 5, I think 5 types of processes, but the first 2 today are isochoric and isobaric. Isochoric is constant volume. Isobaric write that a little more clearly, is constant pressure. So how do we do this? So this, we need a rigid container. All of these need to be sealed, by the way, which means constant N. You can have different moles. You can have the air go in or out. But for pretty much all the things we're going to be doing in this class, the number of moles tends to stay constant. There will be exceptions potentially, but in general, we're going to assume constant N. So you can just sort of like assume that across the board. And I'll be really explicit if that's not the case, which is rare. Anyway, so if I have a rigid container and I heat it up, so heating, what does that do? Well, heating is a positive Q. Q is heat, conduction, positive or negative. Obviously negative if you're touching ice or something colder than the object or the gas. That's negative Q. Heat is leaving, right? If heat is entering, that's positive, right? So heating positive Q increases temperature, which increases pressure. Now I'll refer to your notes on why, but I'll sort of do shorthand here. Why? Well, remember faster. Temperature is faster molecules, remember? Faster means more collisions and more energy per collision. Sorry, I see that's a little scribbly, but I hope you can read that. More collisions and more energy per collision. Therefore, pressure goes up. Well, that means we have a pressure gradient. So we have a delta P pointing outward. But the rigidity fights back. So it's just as a rigid container that is not expanding, right? So a rigid container not expanding, you might have the faster moving molecules inside, right? Slower moving molecules outside, PATM outside. At the boundary, the ones on the inside win, except the container is also pushing back. So we have a delta P pointing outward, which is canceled by the force of the bottle or the container itself, right? So those are equal and opposite. So the net force is 0, but the pressure force points outward. So you just have a pressurized, like pressure cooker. You have a pressurized bottle that's ready to explode, but because it's rigid, it's not. So it's just sitting there, becoming more pressurized. Clearly, that's a lot of potential energy there. Maybe we can do something with that. So this is clearly a useful process to set up something else, which is where we're going with this. So you can start with isochoric. Heating will build up pressure, increases pressure inside by increasing temperature. Great. So the corollary, or the opposite to that, is cooling decreases temperature and therefore decreases pressure. And we can therefore say P1 over T1 equals P2 over T2 for an isochoric process. That's it. So if the container is flexible or not there at all, which we did in class with the hot air expanding. So hot air rises is an example of this one. This is no longer isochoric, is it? This is called isobaric. Now, why is it isobaric? So we have to be careful. When I say constant pressure, I mean beginning and end, not necessarily in the middle, right? So what's going to happen? Well, if I heat up like a balloon of air, right, heater, again, we'll start with heating, but you can do cooling. It's going to have a positive value of Q. Q is heat going into the balloon, into the air in the balloon. Then what's going to happen? Well, same, exactly the same as isochoric, right? So heating causes T to increase, which causes pressure to increase. You can't have that without that. Once you increase the T, you increase the P, but increasing the P creates a pressure gradient outward. And here, because it's flexible or there's no container at all, what does that do? It pushes it outward, so that expands the gas. Because it expands the gas, right? Increasing V, which is the whole point, decreases the pressure. This is a really important point. Decreases pressure back to its original value. We'll call that P naught, most likely like or back to atmospheric pressure if it's in a room, right? P naught is the original pressure. Original pressure. Sorry if that's written, you can hear my words though, original pressure back to P naught. That's it. This is a big deal, which means ultimately it equalizes the pressure. So pressure, flexible container means that the pressure is equalized. Because if it expands because it's hotter, it's going to push out. Pressure did increase for like a microsecond, but as soon as it expands, it decreases back down to atmospheric pressure. So it just keeps increasing, decreasing, increasing, decreasing. It also, so it's like increase, decrease, increase, decrease, increase, decrease, and it essentially just stays constant. Isobaric, a barometer measures pressure. It's isobaric constant pressure. And obviously we could do cooling. T decreases, therefore pressure decreases, which means volume decreases. But then pressure increases back to its original pressure. That's it. So isochoric, we can graph pressure versus volume, constant volume, P1, P2. We start here at T1 to T2. This is heating. And then we can do pressure volume, P1, T1, P2, T2, right? At that volume, and then isobaric. What we're doing here in these graphs is graphing pressure on the y-axis, volume on the x-axis. We're going to do this a lot moving forward. So pressure here, what would isobaric look like? Well, constant pressure. Here we'll have heating. Here we'll have cooling. What will the heating look like? Well, we start at some V1. We'll go to V2. Cooling, we start at a higher volume. Heating T1, T2. Cooling, we start at T1 here. We cool down to T2 here because there's a lower volume. Isochoric heating and cooling. Isobaric heating and cooling. That's the notes. You guys are amazing.